Okay, thank you for coming along. It's probably been a long 3 days. I'm going to try and make this as entertaining as possible. Obviously, with a speech or talk that's got something to do with mutants, there's some scope for jokes. This session is called Better Code Through Making Bugs. I did tell Chris Hansley, who organises the conference, that it was no longer called Mutation Testing, Why You Should Care. I don't think it made it onto the program. But it's the same session anyway, it's just got a different title. Better watch out for that. So my name's Seb Rose. I'm an independent, I guess consultant is the word I would use. But I come from a very long and checkered past of doing software development. I was a developer on Apple IIs when I was a lot younger. I went to university and did computer science. I've worked for insurance companies and banks and engineering companies, and a wide range of people in a lot of different ways. I'm mainly these days working in an area of helping people deal with problems in agile processes. I talk to people about unit testing, test-driven development, and behavior-driven development, specification by example. So that's really where my focus is. Mutation testing is something that was introduced to me by somebody that I worked with at an insurance company a couple of years ago, and I got really quite excited about it because there are some issues in unit testing and test-driven development that nothing else really addresses. So that's where my motivation comes from. I don't blog or tweet much about mutation testing, so if you go to my blog, which is at claysnow.co.uk, you'll get stuff around unit testing, test-driven development. If you follow me on Twitter, you'll get things in the same sort of space with a bit of continuous delivery thrown in for good measure. And if you ever want to get hold of me, the Twitter handle is probably as good a way as any. So having said that, my main focus is agile, TDD, BDD, this sort of stuff. You might ask, why am I here giving this mutation testing talk? And it's because I met these guys. So this is Henry, who I worked with up at an insurance company in Edinburgh. He is the author, maintainer, and almost single-handed developer of a mutation testing library called PyTest, which I'll introduce you to later. Philip van Leyen is Scandinavian. I think he's Norwegian. And he's not a maintainer or developer of a mutation testing library, but he works in that space. He's introduced it to his company. They've used it when they were developing their ballot system for the elections. They used mutation testing to make sure that the test suite was high quality. So he's used it in real world applications. And so both of them very kindly shared with me their knowledge and experience. So this talk is really from 3 people, not just from me. They unfortunately couldn't be here today. So, who writes unit tests? Good, that's the right answer. How do you know that they're any good? No! Okay, so let's try again. How do you know that they're any good? Is there any metric that you use? Is there any technique that you apply in your place of work? What do you do?
Code coverage.
Sorry?
Code coverage.
Code coverage, okay, that's certainly one. Anything else?
I tell people they're really good.
Say that again?
I tell people they're really good.
Okay, fair enough. Well, so there are people that will believe anything, it's true. Peer review, so that's a good one. So peer review is good, code coverage is good as well. So I've got a few, you say you tell people they're really good, so I've got a few targeted answers. So the first one is, only employ coding gods. So then you either know that the unit tests are really good, or you don't need unit tests anyway because the code is always going to work. And of course, every company has got, 90% of its people are coding gods, if you would listen to them. Nobody mentioned TDD. So a lot of people believe that if you do TDD, because the idea is you only write code in response to a failing test, that it means that the test must test what you're writing and everything that you've written will be tested. The downside, of course, is that it's very easy to write code that doesn't actually respond to your failing test. So you write more code than you need to make your test pass, and then your tests no longer cover all of the code that you're implementing. This is going to kill me, that thing there. Peer review, again, is another valid response. So a number of people, a number of organizations that I work with say that they do peer review. How many people have a peer review process as part of their definition of done? So what's the definition of your peer review process? How formally is it specified? What happens in a peer review? Yeah. Yeah. But what do you do with it? I mean, because it'll flash up the changes. Do you go, I don't like that variable name? Do you go, I don't like the structure of this code? This bit isn't unit tested. So that's the usual answer. The usual answer is that we've been told by the agile people that we need a definition of done. So we trundle off to the internet, we go, what's the definition of done? And it comes down, it's got a really handy checklist, and one of the things on the checklist is either you do pair programming or you do peer review or you do both. But we don't go that little step further to find out, well, what does that actually mean? So in my experience, peer review is almost always a waste of time because people focus on curly braces, white space, the occasional variable name, does it have a trailing underscore, and fail to deal with really important things like, if you got run over a bus and I left tomorrow, will the next person who picks up this code understand what it does? So I actually think the most important thing that you need to do in a peer review process is understand the code to make sure that it's independently comprehensible. I think peer review, clearly the sort of peer review that is normally practiced is not going to pick up a poor unit test suite. There are corner cases, there are missing things, and it takes just too much time to look at even a small change to assure yourself that the code is correct. This is the other common response, which is, what's the QA department for? Okay, and the final response is the one that you gave me from the back, which is good code coverage. So code coverage is the standard metric. So all of the others are subjective. Does that flash? Yeah. All of these others are subjective. It's just either saying we're good enough, someone will find it, or the QA department will pick it up. But the good code coverage is the only one that comes out with a number. And I don't know whether you've looked. Well, do you remember Vic Reeves? And who once said that 97.3% of all statistics are made up on the spot. So the reason that joke works is because we believe numbers. And so when code coverage tells us that we've got 80% coverage, we go think, great. That means 20% of our code probably works and 80% of it definitely works. But it doesn't work like that. So code coverage doesn't work like that. So, did that just go backwards? So there's lots of different sorts of code coverage. There's line coverage, branch coverage, statement coverage. Typically we use line coverage in the tools that you plug into Jenkins or cruise control. Line coverage is what you're looking for. And that essentially means each line, or the line, it gives you a percentage of the number of lines of code that get executed when you run your test suite. But if you get good coverage, does it guarantee that you can safely refactor your tests? So who knows what their code coverage metric is for their unit test suite? Oh, okay. 82? 82? Do you feel safe when you refactor your tests?
Not always.
Not always. So I think that's the right answer. So the answer here is nope. Can you trust test suites that you inherit? So if you go in, you get transferred to a new team, you acquire some software from somewhere else, you get a new job, and you look at the Jenkins output and it says 95% code coverage. Does that mean you can trust those unit tests, that test suite, without actually going in and looking at it? How can you guarantee that the tests that you and your colleagues are writing are actually effective? And when you come to legacy code and you go, I'm going to start putting unit tests in place so we can refactor it, so that we can start improving the structure of it and begin to move in a more agile, fast response way. How do I know when I've retrofitted enough unit tests to actually give me some confidence that I haven't broken anything and that when I make some major refactorings, I won't break anything else? And so the question, does it get code coverage? And no, it doesn't. The trouble with code coverage is that it doesn't tell you how good your test suite is. It tells you how many lines got executed. So it doesn't tell us anything about the quality of our tests. So what is it good for? Well, it tells us which statements have been run by our tests. What good's that for us? So it does give you a warm, fuzzy feeling. It does mean that you can run through your tests and it doesn't throw exceptions. Yeah, so it sort of hangs together. It sort of tells you that when you're talking to external services or systems, if you're doing that in your unit test, then you've actually configured it up correctly. It tells you you haven't completely misinterpreted the specifications. So it tells us which statements have been run by a test. It tells us which statements have definitely not been tested. So if you've got 80% coverage, you know that 20% of your code has never had a test go anywhere near it. So it gives you some indication of the breadth of your unit test suite. And I think the warm, fuzzy feeling is really where it's at. The really frightening thing is when management come down and give an arbitrary target that say, we are CMMI level 4, and we will not release any software unless it has 85% code coverage. So there's the law of unintended consequences, and if you force a developer to go for high code coverage, you'll get high code coverage. You won't necessarily get decent tests. So it tells us which statements have not been tested. It is, in fact, very useful for something else. But to ensure that you don't walk out the door, I'm going to keep that a secret. And if you're good, I'll tell you at the end. So let's have a look at some code. So this is a very simple class. So just to make sure that we know where we're at, this is Java. What's my distribution? How many people are Java developers or at least happy to work in Java? A few. The rest of you mainly C#? Anything else? Esoteric, Ruby? Erlang, Haskell, COBOL? Nope. Okay. So even, I don't want to be too rude to you. C# developers should be able to read this and understand exactly what it does. So would anyone just tell me what this is doing? Hello? It does do some counting. What's it counting? Yay! Okay, so there we have the code under test. So this is very simple code. I think you'll agree. Here are the tests. Oh, right, this is, why did I put that in? Oh, right, so we're talking about code coverage. So we've run the code coverage, and this one flags up red, which means we're not testing it. This one flags up green, we're testing it, and this one flags up green too. So our tests are definitely touching these two lines, and they're definitely not touching this line. So we know that this one isn't being tested. So that's already an indication of something. Now here are the tests. So we've seen the code, now we see the tests. So it's like peer review, only you're doing it without the benefit of anyone showing you anything, and you can't jump backwards and forwards between the two. Do these tests look sufficient to you? Sorry? No? What's missing? 10 is missing, good. So, I think that you're a developer, you've spotted the problem. I think in a larger thing you possibly wouldn't have spotted the problem. How would we programmatically or automatically detect that this was missing a case? So that's where mutation testing comes in. Now, mutation testing is something that has been around for at least 40 years. Okay, but it's been around in academia. So academics are the people we never meet. It's just the way it is. They're apparently even more socially inept than developers. So that's going some. I hope you'll indulge me. I'm going to tell a joke which I got wrong at the last place I was at, so I'm going to try and make it right this time. How can you tell an extroverted developer? They're the ones looking at your shoes. So, after dissing developers and academics, I'll move on. A man called Graham Lipton, in 1971, in his paper Fault Diagnosis in Computer Programs, said, if we want to know if a test suite has properly checked some code, deliberately introduce a bug. So this is where we're at. Okay, so we've got some code, we've got some tests, the tests run and they pass. What are the tests for? The tests are to make sure that the code does what you want it to. So the theory goes, or the line of reasoning goes, well, let's make the code do something else on purpose, and then run the tests again, and they should fail. So for me, it was just like a moment of, yeah, of course, makes sense. And they've been doing this for 45 years. And we'll find out later, or we'll talk later about why it hasn't become hugely popular. So at this point, I think, we've really got to the nub of mutation testing. So I'm going to do a bit of terminology, and then we'll go into some details. But if at any time you decide, blimey, it's Thursday, I want to bug off early, that's the main thing here. Mutation testing is about injecting defects into your software automatically and then running the tests again to see if they fail. And if they don't fail, you know that your tests are not sufficient. So a mutation is the deliberate introduction of a bug by changing the code under test. So you can do that yourself. So you can go into your code and you can go and find a branch statement and change its condition. Or you can go and find an increment and turn it into a decrement. That's the sort of thing that those are the mutations that get injected. A mutant is a version of the code under test that has a single mutation. So we don't make multiple mutations in the code because we want to check that the tests catch every possible bug. And if you make multiple mutations, well, you might fail too early, and so you won't know which one has been detected. So you make a single change to the code under test, and you run your test suite. At this point, I want to make it clear that I didn't invent this terminology. It's extremely non-PC. And so I'm going to refer to this wonderful series of books from, I think, the 80s by Patrick Tilley, which imagines a post-apocalyptic world with mutants living out in the radiation zone and purebred humans like ourselves living in big bunkers underground. And what the purebred humans do is they go out in armored carriers and shoot the mutants. And that's effectively what we're going to do now, okay? There won't be blood and gore, but we are really talking about killing mutants. So, mutation test is run your test suite, and if any test fails, then the mutant has been killed. So if it makes you feel better about it, it's like a game. You're trying to kill mutants, and your test suite is your weapon. If no test fails, then the mutant has survived, and that's bad. We want our mutants dead. So I guess if I'm going to be non-PC, then I have to say the only good mutant is a dead mutant. There we go. So that's a mutation test. But that's not enough. We have to do mutation testing. And so we generate lots of mutants. So essentially, we go through the whole of our code base and look for every place we make a decision, every place we do a bit of maths, and all sorts of other things as well, and we inject a fault. And then we run each one through the test suite and record and interpret the results. So recording the results, I'm sure is obvious. We need to know what happened through the test. We need to know which tests we need to know which mutants survived to help us know where our tests are deficient. But equally, there's some interpretation that's needed, and we'll go into that in a minute or two. So here is the code that we were looking at before. As you correctly identified, there's a missing test case. So you see this I is greater than or equal to 10. When we run this through our mutation test, what it's going to do is it changes that greater than or equal to just greater than. This is what's called a boundary condition mutation. And then we run the test suite. And not surprisingly, we'll see it fail. But at this point, indulge me while I try and change resolution and get some code up on the screen, and we'll do it for real, and hopefully everything will be wonderful. So, this is always exciting. Trying to do live coding. I don't know if you were in here beforehand. Sander was doing it, and it's always tricky. You're never quite sure what's going to happen. So, source. So just to show that there's no sleight of hand here, there's real code. That's the wrong one. That's not going to help, is it? Mutation count. There we go. Don't you love these Java long path names? And you get really deeply nested things for just one class. But there you go. So here's this counting class. It's the one that we've seen already. It's exactly the same. It's a carbon copy. Can I make it bigger? So it's a carbon copy of the one that we were looking at in the presentation. And then to go with it, we've got the tests, which again are a carbon copy of the tests that we were looking at before. So that's all straightforward. I then go to a command line, see if that will enlarge as well. And I run ant. So ant is just a build script which does the compilation and then runs the tests. So there's quite a lot of output. Let's see if I can make that a little bit better to see. So we start off, it does all sorts of stuff. It cleans off directories, it makes a directory for the output, it does the compilation, it runs the unit tests, and they all pass. 3 tests run, no failures. And then it moves into PIT. So this is PI test, which I'll tell you more about later. It identifies some tests to be done. It sends the tests off to be mutated. And here are the statistics. So it generated 4 mutations, but it only killed 3 of them. So we know really already which one failed. But it then goes into more detail, and it says that the math mutator killed its mutation. So math is a mutation which does stuff when you add things and just subtract things. The conditionals boundary mutator didn't kill its mutant. So it's the conditions boundary that the problem is with. The conditions boundary is where we checked, we mutated it from being greater than or equal to 10 to being just greater than 10. And that's where the failure happened, because we had it 11. And that's both greater than equal to 10 and greater than 10. And we've got a returns value mutator, which changes the value that's being returned. So that mutated the value of the count being returned. But that got caught because I'm asserting for the value of the count. And then we've got a negate conditionals mutator, which is where you actually turn if it's true to being if it's false. And that also failed. So we got a lot of things and we got them killed. So this is all very well. This is text output. But of course, no tool these days is complete without some graphical output. So we'll just see if we can run that up, just to give you a flavor of how detailed it gets. Pit reports. Where are we at? This is 1422. Can you read that? Yeah, at the back, you okay? So it tells you that the line talks about the line coverage, which is 71% coverage. Mutation coverage is 75%, and in this case, coverage means the number of mutants that got killed divided by the number of mutants that were created. So 75% of the mutants got killed. And then a breakdown by packages. So if there were, typically our projects are slightly bigger than this, and so you can then drop down into the package, and then you see the classes, and then you can drop down into the class, and you begin to see a full output showing you where the problems were and what the issues were. So what it's saying here is that if I is greater than or equal to 10, well, that was a changed conditional boundary. A mutant was injected by changing the conditional boundary, but it survived. There's also pale red down here, which says that this method, it wasn't tested at all. So, for purely pedagogical purposes, I'm going to just create a new test. It should count integers equal to 10. Does that sound about right? So if we pass 10 in, then the test count should be 1. Now, of course, I'm being bad here. I should always write a failing test, but being bad is one of the things you get to do on stage. So we'll run the tests again, or run the whole build again. So in this time, we killed them all. So that's good stuff. We can go and have a look again at the output. and again drill down, and the output this time will show that all the mutations got killed. We've got green everywhere. We've still got a red here in this reset method because I'm not testing it at all. Now, I can run tests against it. That's absolutely fine. It doesn't actually do what we want it to at the moment, and I'll explain why in a second. So the test that I'm going to write here is reset should set count to 0. So we test count, and then we do testd reset, and we are expecting this to be 0. Yeah? So then back into command line land, and then rather than going in there, we'll go into the so here we've got, it hasn't changed. So we now no longer have red here, but there's no mutant being generated. Now, this is because the mutation that would modify this is not enabled by default in PyTest. And the reasons for that are to do with the fact that it takes too much time, and there's basically a set of 7 stable mutations that PyTest enables by default. I can go in and fiddle with the config, so it would generate a mutant for this as well. That's much easier in Maven than in Ant. I'm not going to go and fiddle with Maven, mainly because I never want to do anything that needs to use the network in a conference environment. So I'm going to leave that there. Are there any questions about what you've just seen? So I went through it quite quickly. Does it make sense?
Is PyTest literally going to change the source code?
We're going to get there.
Okay.
Yeah, no, that's the next segment. I just wanted to show you it working before we moved on. Essentially, there are many different ways that the different tools mutate the code. And we'll talk about why PyTest is the gold standard.
Generally, the mutations are all automatic.
You don't touch them, no. So any mutation framework worth its salt is doing that for you. If you have to write them yourself, you might, yeah, there's no guarantee that you'll do them all. So what do I need to do? Go back. I should have shown that, shouldn't I, first, or did I? So it says demo time, but you see, I can see it in advance here, and so I knew that it was coming. So this is, PyTest, as I said, is written by Henry Coles, and this is his advertising copy. And later on, we'll explore and see whether that's really true. So these are the mutation operators that are available in PyTest. And you've seen the conditionals boundary mutator, you've seen the negate conditionals mutator, both of those have been put in, and we've seen a math mutator. There's a funky one called remove conditionals mutator, which isn't enabled by default, which actually just goes, if there's a conditional, it just takes it away. And you know, an incremental mutator, it turns that into a decrement. Invert negatives, as if you do a minus sign, it'll turn it into a positive sign. So you know, they're fairly simple mutations. The one that we didn't see is the inline constant mutator. That one needs to be turned on. But you can do funky things by non-void method calls mutator. And the interesting one for me is the void method calls mutator. It says if a method has a void signature, it doesn't return anything. Tell you what, we just won't call it and see whether anyone cares. So you know, there's some really very simple changes, but really quite pervasive. You know, a very simple thing can break your software. And what's been observed by the academics, because as I say, this has been living and breathing in academic land for a long time. What's been observed by the academics is that generated mutants are similar to real faults. As in, these really are the sort of problems that we create, that we make for ourselves. Because the gross problems we'll probably find. We might see them in, they're the sort of things that will come out in a peer review. It's the subtle things that kind of disappear and fall between the cracks. So this was research from 10 years ago, and then this is from a little bit longer. And this one, I guess, seems straightforward as well. In practice, if the software contains a fault, there will usually be a set of mutants that can only be killed by a test case that also detects that fault. So this isn't it's an assertion. The paper itself doesn't put forward a mathematical proof of it. So it seems like common sense, but it's not mathematically proven. And yeah, what's the title of this paper? Estimation and Enhancement of Real-Time Software Reliability Through Mutation Analysis. So, what to get your teeth into in that. And finally, complex faults are coupled to simple faults in such a way that a test data set that detects all simple faults in a program will detect most complex faults. That again has no formal proof. It seems reasonable to believe that that complex faults are made out of lots of simple faults coming together. There are going to be environmental things that potentially your unit test suite is never going to pick up. So for instance, this is not going to work if you're dealing with threading type of activities, or if you're looking at trying to do integration tests against external systems. There's a whole domain of potential faults that this mutation testing isn't really going to help you with, but in the same breath, there's a whole domain of faults that unit testing isn't really designed to help you get either. So no one's ever going to tell you that unit testing is the only sort of testing that you need to do against your software. It's not going to help with usability testing, it won't help with performance testing, it's not designed to help you with load testing. So this is not the only way forward, but if you're familiar with the unit testing pyramid, is that a concept that most people are familiar with? Yes? No? No. Hand up for no. Hands up for no. Okay, I'll do it very quickly then, if I've got a pen, because it's one of my favorite pyramids. Thank you for laughing. So, it's not only is it one of my favorite pyramids, it's not a pyramid. So that's what makes it even better. The unit testing pyramid is a triangle, but you have to imagine it being a pyramid. And so the breadth of the triangle is roughly stands for the number of tests that you've got. So the wider it is, the more tests of that sort you have. And the height of the pyramid says the depth of stack, or depth of application stack. So the higher you are, the more of your application you're executing at any one time. So the stuff that's at the bottom is your unit test, the things that we're talking about today, the foundation of your developer testing, your testing strategy. And then as you go up, you sort of get integration tests. And then at the top, you have end-to-end or system tests, which will go through the UI or the service layer and all the way through to the database. So you have fewer of these and more of these. And what we're really saying is that the unit tests, which are the things that we write the most of, are the things that the mutation testing is helping us verify as being of good quality, exhaustive enough. Because the mutation testing is going to go through our entire code base and inject mutations everywhere. Now, I say everywhere, almost every mutation testing library allows you to configure that. So what we'll see in a minute is that, actually this can be a slow process. Because if you have lots of code, it means you've got lots of statements. You've got lots of statements, you've probably got lots of conditionals, constants, assignments, branching, etc. Which kind of leads me to the next slide. Why has mutation testing been almost entirely ignored in the commercial world? And it comes down to these two reasons. Historically, it's been very poorly performing. And we'll go over some back-of-the-envelope calculations in a minute to show just how bad can be. And secondly, equivalent mutations, which are something I will cover in a short while. So these are the two main reasons that have been voiced by both practitioners and academics as to why it shouldn't be or isn't suitable for mass adoption. So how bad is performance? I'm afraid it's time for another bad joke. We're going to use Yoda time as our example. And so it's probably pronounced Joda time, but anyway. Joda time is a date library that ships well, not ships with Java, written in Java. And the reason Java's got a date library is because its handling of dates is really bad. Really bad. So .NET might have copied a lot of what was in Java, but they made a lot of it better. And now Java's borrowing some of it back. But Joda time, it was the way people got around the fact that Java date was just so bad. So Joda time is a small library for dealing with dates and times. Now by small, what do you think small is? What does small mean to you? How many lines of code? Pick a number. It's Java. So it's small, but it's only small relative to things that are big. You know, you don't knock something like this out in a day. This is the output of many months, many years of development. And you know, date and time actually has a lot of complexity. You've got all those time zone things. You know, I say that actually, given that I've been slagging off Microsoft, I should do this one. So this is a phone. What sort of phone is it? It's a Windows phone, okay? So I might slag off Microsoft, but it's a Windows phone. But it has one very bad problem. And it's when you create an appointment in a calendar, it then miscommunicates with the server and pushes it an hour forward. And this is really bad. Microsoft have been unable to sort that out. So maybe they should use Joda time in Java instead. Who knows? So it's a relatively small library with 68,000 lines of code, and there are 70,000 lines of test code. So that sounds pretty good. So typically, you would expect I would expect in a well-tested library to have about as many lines of test code as there are of actual implementation code. So that sounds pretty good. It compiles quite quickly on a standard machine. So on my machine, it takes about 10 seconds. And it takes about 16 seconds to run the unit tests. So it's all good. But let's bring in mutation testing. We're going to use all 10 of those mutation operators that I talked about. So let's say that generates around 10,000 mutations. So you know, that's not going excessive. There are 67,000 lines of code. We're going to use 10 mutation operators. So we're really saying that we'll find, you know, 1 in 7 lines is susceptible to a mutation. So we're going to generate 10,000 mutants. I'm going to assume that the compiler can optimize things. You know, that if I've compiled it once and I make a small change, it would be able to compile it again faster. So rather than the 10 seconds of compile time that I was talking about, there's just 1 second of compile time per mutant. So this is, as I said, just back of an envelope stuff. So this means that it will take 2.5 hours to generate and compile 10,000 mutants. So if you want to plug in 1 second and multiply it by 10,000 and then divide by 3,600, that's sort of what you can. But, of course, you have to run the test suite for each mutant. So we've got 10,000 mutants. The test suite takes 16 seconds to run. So this sounds pretty bad, doesn't it? This is a small library. We don't want to hang around for 47 hours while it crunches through this mutation testing. And actually, the best time to run mutation testing is on your desktop while you're developing. So if between each run of your test suite you had to wait 47 hours, you might not get that much done. And so you begin to understand why it didn't immediately transfer from academia into the public, the public domain of commercial usage. So, the academics who were doing this back in the day, they were doing it on bigger code bases. Because they were academics, they were more interested in the mutation operators. No one was paying them. And so they were using far more than 10 operators. And back in the day, of course, they didn't have the computing power we had today. So actually, they would fire it off and come back in a week or two. Yeah. And that's really how they were doing it. And that's what most of these papers are based on. But Henry came along, and he'd seen a number of different, there have been quite a few attempts at commercializing this. Open source commercializing, not actually trying to sell it, but actually trying to make it usable. And Henry, I think, has just had some really good ideas. So he went, well, if it takes too long to compile, let's not compile it. So that's one of the benefits you can do in Java. and potentially you can do in .NET in that you get bytecode. So once it's compiled, why not mutate the bytecode? So PyTest manipulates the bytecode directly. Now Java apparently, because I'm not on the implementation team, Java has a very good set of APIs for manipulating the bytecode. And he reckons, and in fact, I don't mean he reckons, I've seen the output. He generates about 10,000 mutants in about less than a second. Pretty good going. So that's taken 2.5 hours and put it down to a second. That's a good order of magnitude. There's still the slight problem of 10,000 tests, 10,000 mutants that need to be run through the test suite that takes 16 seconds per run, which is 44.5 hours. So what's the best way of cutting down on the time it takes to run your test suite? Parallelization is one good answer. Correct. Run fewer tests. So he made what I think is quite a clever leap. I don't know if it's genius, but it's a clever leap. He started by trying to run fewer tests just very simply. So when a test fails, as in once you've caught that mutant and it's been killed, don't try the rest of your test suite, so you can stop earlier. So on average, that might halve the runtime. So that's a good start. So now we're down to 22.25 hours. Probably quite a lot better than 44.5, but still not very good. Then I was thinking about, well, maybe I can just choose some of the tests to run. Choose your tests carefully, because not every test can kill every mutant. So that seems like a promising way to go. And equally, as you were saying, parallelize the test runner, because unit tests are supposed to be able to run independently. They have no dependencies outside of themselves, so you should be able to parallelize them and make use of the fantastic 2 cores that I've got on this machine, or the 16 cores that you've got on your telephone. So yeah, your tests are unit tests. Choosing your test well is the critical bit, because there's only so many cores you can throw at the problem, and actually if you need half a dozen 32-core machines and something to coordinate dispatching it, you're probably looking at more investment than most companies are willing to put into this sort of space. So that, although it helps, it's not the answer. It's not the only answer. And stopping running the test halfway through is only ever going to give you, one order of magnitude saving, if that. So we have to choose those tests well. As I said, each mutant can only ever be killed by a subset of the tests. And that means that every other test you run is waste. So how might we know which test might kill any given mutant?
Well, when you have a test class for don't want to automatically with a class on the test, so you adopt a convention.
Naming conventions, that's one. Good. So we didn't. So you skipped over the other one that I had. What I should really do is have something like out of QI. When people say things that I've got pre-prepared, it goes, anyway. So static analysis is another way that people have tried to do it. So the problem with convention is that you have to work according to the convention. And if you flaunt the convention or you want to retrofit it, it becomes problematic. Static analysis is another way of working in that you can run tools over your code like checkstyle or fxcop that will tell you some of the pathways that it will go down. But static analysis misses out on a lot of dynamic type stuff, dependency injection, late binding, all sorts of funky stuff that you actually want to test you really do want to test. So the one that really wins is coverage data. So as I said, this is what coverage actually turns out to be really useful for, because what does coverage tell you? It tells you which tests touch which lines of code. And so then you're going to extrapolate back. I've mutated this line of code, therefore these tests could potentially kill this mutant. And you only run those. So as an example, so you may have seen this one before. And we've got our coverage stuff here. So it's done the coverage analysis. And so now we know which lines of code are run by which tests. And so PyTest can say, this line of code is only touched by should count integers above 10 and should not count integers below 10. So these comments are done before I added those 2 tests that I added interactively. This test, it's not even. I just made a mistake. So this should count integers of exactly 10, should in fact be up in the one above as well. That one, not covered by any test. Well, actually it was now, wasn't it, because I added one, but there you go. And then should start with empty count, doesn't cover any of the lines shown because it's implicit. There's no code that actually sets count to 0 to start with. So armed with this knowledge, we can dramatically, well, I say dramatically, we can shrink the number of tests that need to get run against this code. Now, imagine you've got 10,000 tests. Well, for each mutant, there's only going to be a handful of tests that run through that path. You certainly don't want unit tests that are traipsing all over the code base. Doesn't sound like a unit test. So you can really decrease it by at least 1, if not 2 orders of magnitude. So Joda time, which we talked about earlier on the back of an envelope, running in 47 hours, this is what happens when I run it on my machine. So it does generate 9,922 mutations. Only 79% of those get killed, but it ran it in just under 10 minutes on using 2 threads. So this is, it's not a bad machine, but equally it's not a killer server. And you can begin to see that you're moving it into the space where you could actually run it, certainly as part of your CI build, certainly as part of your overnight build. We're not quite yet at the space where you would want to run it on your developer desktop every time you typed in another line of code. But maybe we'll get there. So we'll cover that I think I'm covering that in a little bit later. If not, I will mention it. Okay. So you're ahead of me. There is PyTest has a source code integration module which does exactly that. The intention, the way that it's intended to be used is that you run it on your desktop and it checks what's been changed in your environment against what got checked out of source control, as in basically it does a status or a diff or however you want to think of it, and then only runs tests over those lines of code or those packages. And that brings it right down again. But my only 79% killed. What I've talked about so far, it sort of describes some of the reasons that things get killed and not killed, as in there are no tests that cover them. Can you think of any other reasons, that mutations may not get killed, apart from the fact that your tests are rubbish?
Semantically equivalent.
Sorry?
Semantically equivalent.
Semantically equivalent. Yes. So we've got missing test cases. I do have semantically equivalent in a second, but I need another moment. So what might happen if you've got a loop and you change something in the loop? What might happen to that loop? Yeah, or it keeps executing. So there's a whole class of tests, or a whole class of mutations that don't terminate. So you can't kill them as such. You have to just, or rather, you have to do exactly that. You have to kill them. You have to kill the process, because otherwise it'll do your stack overrun. It'll loop there forever. So there's a category of failures that it's difficult to know whether to account for them as killing the mutant or not, because did you catch the defect, or did you just not cope with it? So there's timeouts which are part of PyTest. It will wait a certain amount of time before going, nah, this is never going to end. One of the issues, if you have big maths calculations or something that does take time, then your timeouts become an issue, and you have to tweak its internal notion of how long is too long. And as you said at the back, there's the semantic equivalent, so equivalent mutations, which I had promised to talk about. So I'm going to talk about them just now. So we've got this code here. And I'm going to, let's demo it. Let's demo it. Oh, that's a bit flickery. So, where am I? Go back down the path. So it's very simple code, and you can already probably see where the issue is going to be. And there is the test. And the test is basically going, it should throw an exception if the number is less than 100, but it shouldn't if the number is greater than 100. So, okay, so then let's go and dig around in this bit. Where am I? So same difference, different class, and here we've got a lot of issues. We've already got a boundary condition that's survived, and we have to ask ourselves: is it survived because it's a bug, or is it survived because we have an equivalent mutation? Because actually, at this point, I can never be 100. And this is one of the issues that the academics picked up on. They said, there's a whole class of mutations which cannot be killed, and you have to go and have a look at your at the code itself to determine whether the mutation is an equivalent mutation or a valid mutation. So, has the mutant survived because there's something semantically wrong in your software, or is this mutant survived simply because that branch of the code couldn't be exercised properly by your current structure? Now, we can do a number of things here. I'm not actually going to do any of them because I think we'll just deal with it theoretically. But the point is that there is a class of problem here that needs to be, you need to understand exists. Just because a mutant has survived doesn't mean you've done anything wrong. However, I say that, maybe we should do this. So, how would you change that code now that you know that there's an equivalent mutation that could never get here? Sorry? Remove the if. So what has this mutation shown us about the structure of our code? So it's shown us that there's a completely redundant check. So it's not that we were crap. That maybe these were in different methods and that they were chaining and we just didn't realize it. But the mutation testing, if you go in and check on your mutants that survive, it can lead you to restructure your code so it's better designed. It gives you some clues. So what happens when we do this now? Looks better. There's still a boundary condition where it survived. I guess I haven't changed the test properly. And it removed this call to do something, and it didn't fail because do something doesn't do anything, so it lies. So it's telling me a few things. One, I should make better test examples, I guess, and the other is that I still need to sort out my boundary condition. Share. So it's mutated. This is one of the mutations that it did, and it can never be 100. So that's why we saw that. And again, as a clue to me to do that demo, which I missed. So this is what we demoed. We should have written something along these lines because there's absolutely no point checking that it doesn't pass in one point and then checking that it does later on because it couldn't possibly because you've exited with an exception. Which actually brings me back to one of the first Java jobs I ever did back in 2000. It was for an internet bank, which is now, it still does sort of exist. It's called Intelligent Finance. Apparently, once upon a time, they thought that all banks would be built this way. And they brought in a lot of consultants from Ireland. And these were consultants of a different flavor from the consultant that I think that I am. They're the consultants that have just left college and they're being charged out at 800 quid a day and being paid 50 quid. That sort of consultant. And she was a lovely woman, but she clearly didn't have a background in coding. And so I came across this beautiful piece of code which said, if true, then do this, else, if false, then do that, else. It's like, yeah. I thought to myself, I'm not sure that Java's got ternary logic quite like that. And so that's the sort of thing that mutation testing is going to show to you, because it's going to try mutating something in that last else, and there's no way it's ever going to get there. So some causes of equivalence that that have been identified is dead and useless code. So if you mutate something that isn't being called, if you have a whole bundle of stuff in your code base and you decide to edit it out because you just want to save it for later, it'll find that. It'll find non-functional modifications. So if it does if there's some optimization that you've got for performance reasons in your code, and it fiddles with that, and the performance goes down, it's not going to find that. That's an equivalent mutation, because the output is going to be exactly the same. It just will take longer. I guess it might time out, but that's a side effect. Unsatisfiable guards, these are the things that we've just seen. This is code which, although it's potentially reachable, the semantics of it make sure that it can't actually get there. The input conditions are never satisfied. And there's internal state that maybe isn't surfaced externally. I think it will pick up a number of internal state ones. And as we saw in that example, by following these clues that the mutation testing is giving us, so we can either find out that we need to write another test case to try and kill the mutant, or we can see that we've generated an equivalent mutant, and it can lead us to consider whether our code needs to be restructured in some way. I think that's just restating what I've stated already. Mutants that survive need to be checked manually. So this is one of the main reasons that the academics have given us for not using mutation testing in practice. But in the time that I've been using mutation testing, and from my colleagues who use it have been using it for much longer than me, they say that this is not all that common in practice. So from their perspective, even running it over Joe time and going through and looking at I don't think they've looked exhaustively at all 2,000 that passed, but looking at it, a sample of them, they weren't finding many that were due to equivalence. Most of them are due to missing test cases. Now, that may be a bad thing, but nonetheless, what it's saying is that it's not going to be a showstopper. It doesn't happen. You don't get 5 equivalent mutations for every line of code. You get a very small proportion of equivalent mutations. And so, given that anyway, we know that going for an absolute value of any number is always going to be gained and is a bad thing. So let's not worry about it too much. That's a laissez-faire, lackadaisical approach that we've taken so far. But what I found, because I do generally work in a test-driven approach, is that actually because TDD does typically force you or require you to write the test before you write the code, and only to write just enough code to pass the test, you very rarely get into a situation of the nature that we've just been looking at. Now, it's not, I earlier said that TDD doesn't save the day every time, and it doesn't save the day every time here, because there are times when you come in and you're refactoring an existing code base, and you'll be changing something that has dependencies further down, and you may not have tests that cover that at that point. So, TDD helps, and it's not that common in practice, and as I said, we need to tolerate a few survivors. So, as I said, the Joe time, 67,000 lines of code. That's a small code base. What about bigger code bases? So, one guy had to go with an Apache project called Common Math, which is a set of mathematic, things that do big number crunching. Excuse me. Did that come out very loud? Oh. And it's got 177,000 lines of code, 109,000 lines of test code, It takes about 8 minutes to build it and run the unit tests. And it generates a lot of mutations of the math code, because it's got a lot of maths in it, not surprisingly. And he finds that on a machine with 4 threads, so he's got 4 cores to spread it over, it's taking about 1 hour and 15 minutes to mutation test in full. Again, you're not going to do it on your desktop. And at that point, it's got line coverage of 92%, which is pretty good, but I guess maths is maths, isn't it? And mutation coverage is 79%. So that's quite big. Already we've got to a point where you definitely aren't doing it on your desktop before you check in. So mutation casing can take a long time. So we could use fewer mutants. So we've got the ability to scale up or scale down the number of mutants that we enable on our tool. 7 is the default number. There's 10 standard ones in PyTest, and there's a few experimental ones to add on. You could scale it down. It's probably not a good idea, but it's one possibility. You could filter the candidate zone of your tests, so you can partition your build. Maybe when you're working on your desktop, you're generally working in a particular area, so you would only run through PIT the tests that actually apply to that area. So you probably partition your unit tests like that anyway, according to the convention that you're talking about. You can run it less frequently, so you don't do it on the desktop, you do it overnight, you do it before the release, you do it in a stabilization mode. Again, not ideal. But essentially, we would really like the developers to be doing the mutation testing on the code that they're working on, because it really does give you some clues very quickly about how your development is going, how your design is evolving, whether there's some gaps in the space, whether your unit tests are effective. And so it's something that gives you feedback immediately. And so fast feedback is always good and improves the design of the code. You can get your CI server to run the mutation tests, and ideally that will be over the whole code base. Again, it's to do with how much feedback you've got, how many stages you have in your continuous integration pipeline. Quite possibly, you've got a dev build that happens as soon as someone checks something in. And at that point, you wouldn't want to run 3 hours of tests, because you want your developers to get feedback if they've broken the build much quicker than that. But you'll probably have an integration environment that only runs on a slower cadence, a nightly build, so that might be the right place to do it. Or, as you pointed out, there's an SCM integration that you can use. So PyTest integrates with some SCMs, and I can't tell you at the moment which ones, because I don't know, but Git is one of them. So, at this point, I'm going to just take a breather. Has anyone got any questions at the moment? Yeah?
Is there anything like this for .NET?
That's coming.
Same thing. Do you know if this works with Android, or is it pure Java?
This is pure Java code. I'm not going to be definitive about that, because I don't develop in Android, so I don't know. But it does use Java bytecode is what it mutates, and it uses the Java API to do that.
Is there a way of getting it to ignore the mutants you can't kill because of the reasons you've mentioned before? Because if you put it through a CI server, and the condition for passing is that all the tests pass.
So its output can be configured. It doesn't necessarily fail the build just because the mutant survives. So yes, you can tweak it like that. You can fail the build on a given percentage if you want to. Typically, you would just use it as feedback and watch the trend rather than have it fail the build because of the equivalent problems.
Have you had any thoughts about pushing this into the cloud? So obviously from a timing and compute point of view, spin up people.
Yeah.
Crunch it.
So I don't believe that's currently on Henry's roadmap, but equally it doesn't seem like something there's a huge barrier to doing, because it's not something that you would necessarily have an issue with. I mean, there is the distribution of the distribution of the test to the slaves, and I guess that's the area that one would need to look at. I can tell you that it's an open sourced project. Henry is always looking for willing, keen volunteers, so that's a great idea. I'll grab your email address afterwards. Yeah. Actually, though, I'm sure you pick it up. Anybody else? Okay. So I'm going to give you some experiences and recommendations. This is a distillation mainly of Philip's experience, because he's tried quite a lot of different mutation testing tools in his journey. So not surprising, like any way of working, it's much easier to do from when you start doing a project than to try to retrofit it. It's hard to retrofit unit tests, and it's hard when you find that you've got lots and lots of surviving mutants to then go in and really feel like you can invest the time in removing them. Same as with unit testing or TDD, start with something small, because a little bit of success gives you the confidence to keep going, a little bit of success gives your organization the confidence to keep going. So these two things go hand in hand. What we found is that if you design your code well, then it becomes much simpler. It's not surprising that. And so if you're looking at a good object-oriented design, then what you're going to have is lots of small classes that are highly cohesive and loosely coupled. This is just standard O stuff. And if you've got that sort of behavior, that sort of structure, then you won't have that many unit tests per class. And if there aren't that many unit tests per class, there aren't going to be that many unit tests that are candidates for killing off mutants in that class. And so you're only going to, at the worst case, have to run a few. You're only going to have to run a few tests for every mutant that's generated. So it's synergistic. If you design your code well, then it will be quicker to run the mutation testing. Select a good tool. Now I thought about taking this bit out because mutation testing is an idea. I really wanted to get across the flavor of why you would do it and to try and get people interested in it as a technology and to see how poor coverage is as a measure of quality for your tests and to start thinking about other ways of doing it. Having said that, there are an awful lot of bad mutation testing tools out there that actually don't work or not fit for purpose. And so selecting a good tool is important. You need to be able to configure it. You need to be able to decide which mutations you want. You need to change the timeout. You need to be able to select subsets. And these are all to compensate for the fact that with large and growing code bases, you get into a point where it's no longer tenable to run the tests on the desktop. Same for why you want it flexible. There are even some frameworks out there, they'll tell you that mutants have survived, but won't tell you which ones. This is not helpful. It's like, I think in my previous talk today, I had a quote from Jerry Weinberg, who wrote a brilliant book called Myths from Software Testing, something like that. And it says, testing software is the art of exercising it and getting feedback from it with the intention of doing something about it. And so if you can't do anything about it, there's not much point testing it. Now, this might come as a surprise, but his recommendation is believe the tool. Now, I completely understand this because I started playing with a .NET mutation testing library a month or two ago, and it was throwing up an equivalent mutation. It was throwing up a mutant that it said had survived, and I just couldn't see it for the life of me. It just wasn't there. I was going, this thing's broken. So I later discovered that this thing was broken, but that bit wasn't. That bit was me. It was a temporary variable in the test, and it had decided to mutate that. Crazy stuff. So it might not have been broken, but it was certainly not being very clever. And eventually, just by moving it in line, that equivalent mutation disappeared. So once you've found that once you've decided that you're going to believe the tool and it's telling you that this mutant's surviving, then you have to work out why it's surviving. If it's equivalent, try and work out if you can refactor the code to remove that equivalence. If it's a missing test case, try and put the test case in. And in the end, I guess give up, I'm afraid, is the thing. Like so many things in life, you can turn it off, and you will then never get the benefit from it. So the world is full of unit test suites that don't run, Compiler warnings that don't fail the build. Who has got compiler warnings that fail the build in their organization? One. Some projects. So you think to yourself, oh no, why did we do that? Who's got, I don't know, style check software that gets ignored? So, I mean, it's pervasive. You know, we think, oh, this is going to be a good idea. It'll really help us. And then, oh my goodness, is it that bad? Oh, we'll ignore it then. So don't turn it off. But, you know, actually, before you start turning mutation testing on, probably compiler warnings is a better place to start. Anyway, don't get me started. Less code. This was Philip that was saying this, but, you know, Kevlin, who I think was talking here earlier in the week, Kevlin Henney? Yeah, so one of his favorite things is that he says code is a liability, not an asset. So the less code your organization has, the better it's going to do. I mean, obviously the code that you've got needs to be really hot, but if you can get rid of it, that's great. More unit tests, that almost goes without saying. But he also says more intelligent unit tests. So I've got a lot of things to say about unit testing, not today, but the thing about unit testing is that it's not as simple to write a good unit test as we would like it to be. Unit tests are hard to maintain, unit tests cost a lot to build. There are some techniques and some concepts that are really handy to pick up, and yet unit testing is not taught very often. So I don't know, did anyone get taught unit testing at school or college or university? Yeah? Go on, tell us about it.
Well, we had to do a group project on one of those Lego NXT
Okay.
robots. So our project supervisor said that we have to use unit tests because that's what we're going to use in the industry.
Impressive.
He's not a lecturer anymore.
Okay. So I wonder what that says about it. Okay, so don't do unit testing if you want to keep your job. Maybe that's that message. So tools. Ruby has got Heckle and Mutant, and probably others, because Ruby is like that. It just spawns off. It's full of a community of people who apparently have nothing better to do than write open source tools. Mutant is written by a guy in Essen called Marcus Scherp, who I did some work with a couple of months ago, and we did a workshop and he was dealing with the Ruby people, and they seemed very, very happy with it. So I haven't used it myself, but it's out there, it's actively maintained, he's still developing it, and people that use it like it. Java has got a number of different tools out there, of which PyTest is the one that is most up-to-date, most maintained, and there's no reason to use either of the other ones. Jester was in fact implemented by a guy called Ivan Moore, who's a member of the sort of agile community in London. So if you ever go to, does anyone here go to Extreme Tuesday Club? No? So have you heard of the British Computer Society? Have you heard of XP Day? No? Okay, so London's got two great communities, and they actually overlap. There's the British Computer Society, which has the Software Practice Advancement Group, which runs the SPA conference every year in Southampton Row. And then there's XP Day, who run a conference every year as well. Generally, they say XP Day, not just XP, not just one day. There you go. So there's requirements, and they sort of meet up, and there's a meeting every Tuesday night in the Bishop's Finger, Smithfield, where you sometimes get presentations, but normally you can just talk about the latest geeky thing that has taken your fancy. So there's a lot going on in London if you have the chance to pick it up. So here I'm delaying it because I know you're a .NET audience, and the next one is a C# bit, and I'm afraid there's bad news. There are 3, and they're all awful. Nesta is not supported and is unusable. Ninja Turtle is not supported and is barely usable. Cream is apparently usable. It's not had any releases for over a year, which is never a good sign. And I was having a discussion with Henry about this because, you know, he's a Java programmer, and I was thinking, well, you know, they've both got bytecode. You know, the rest of the stuff is going to be the same. You know, you can translate from one algorithm to another. It's taking coverage data, tracking through the path. He's not a Java programmer. He conjectured that possibly the API through onto the bytecode and the abstract syntax tree was more fully fledged in Java. Now, I find that difficult to believe. I don't know if any of you not .NET developers have ever delved into manipulating bytecode at that level. No. So it's crying out for it, because both times I've done this session, there have been a substantial number of .NET developers kicking about. It's clearly not an environment that's, well, actually, no, I say that, it's Microsoft, isn't it? It could disappear tomorrow, couldn't it? But it doesn't look like it's going to. It's got some traction. So it's surprising, at least it surprises me, that no one has actually made this one stick. There's also Pester in Python and a wealth of other ones. And so I've got at the bottom a link through to a survey, a Wikipedia survey of which ones there are. But really, the only two that I've had any real experience with are Ninja Turtle and Python. And Ninja Turtle, quite frankly, caused me to pull hair out. So it's not supported, as I say. I did have some communication with the original developer, who then stopped answering my emails. I wasn't rude. I just said, why is it not working? Maybe that's the wrong thing to say. And I had to copy DLLs around the place, and I had to put things in the right folder, and it wouldn't run from the command line, and the integration with Visual Studio was a bit iffy. So you can play with it. If you're going to play in C#, I think probably try Cream first, because although I haven't had any personal experience of it, that's the one that a couple of .NET developers have pointed me to in the past week. So maybe next time I'll be able to say more about it. However, PyTest, is really good. So maybe you should just move to Java. So it works with loads of different bits of Java, integrates with all of the standard build tools. It's got plugins for the common development IDEs. It plugs into the common CI servers. Strangely enough, we haven't got on here the SCM systems that it plugs into, so that's clearly an omission. And Henry, he has got a family, a young family, and a job, but he still seems to manage to get a release out 3 or 4 times a year. So, when you're trying to pick up an open source project and you're thinking about, am I going to recommend to my team adopting it? The fact that someone or a team of people is actually actively maintaining it and evolving it is always, for my money, should always be high on the agenda in your questioning. It's also widely used. So I talked about the Norway's e-voting system, so he must be Norwegian, there you go. But it's used by Sky, it's used by some banks, biotech companies. So not all of these people are mission critical, people lose their lives if it fails. Some of them just want to assure themselves that their tests are doing what the developers think their tests are doing. And it's made in Britain. So that's good. Although I should point out that on September the 16th, there is a vote, and it might be made in Scotland. That's basically the end of my session. I just want to advertise to the very few Java developers here that I'm writing a book at the moment called Cucumber JVM, which will be out maybe later this year. And so if you're in Java world, JVM world, and you would like to do a bit of behavior-driven development, Cucumber, that's the great place to start. Thank you for your attention, and I'm happy to take any further questions.